What if everything you learned about the speed of light is based on an assumption we cannot prove? You've heard it countless times. The speed of light is exactly 299,792,458 meters per second. It's in every physics textbook. It's carved into the foundation of modern science. Einstein built his theory of relativity on it. GPS satellites depend on it. Your smartphone wouldn't work without it, but here's what they don't tell you in those textbooks. We've never actually measured it. Not the way you think. Every measurement of light speed ever conducted, from the 1700s to today, has one profound limitation. We measure light traveling there and back, out and return, forward and reverse. We calculate the average of the round trip and call it the speed of light. But what if light travels at different speeds in different directions? What if it races toward you at infinite velocity and crawls away at half the speed we think it has? What if the universe has a secret asymmetry we've never detected because we've been asking the wrong question? This isn't science fiction. This is one of the deepest unsolved problems in physics. The story begins in 1676, when Danish astronomer Ole Romer first demonstrated that light has a finite speed by observing Jupiter's moons. Over the next 3 centuries, scientists refined the measurement with mirrors, rotating wheels, and laser beams. Each experiment grew more precise. Each result converged on that same famous number. But every single one had the same hidden flaw. To measure speed, you need distance and time. Distance is easy, you can measure it with a ruler. But time requires clocks. And to measure the one-way speed of light, you need 2 perfectly synchronized clocks, one at the starting point and one at the finish line. Here's the problem that changes everything. You cannot synchronize distant clocks without already knowing the one-way speed of light. Think about it. How do you sync 2 clocks a mile apart? You could carry one clock to the other location. But moving clocks experience time dilation. Einstein proved that. You could send a light signal to synchronize them. But that requires assuming light travels at the same speed in both directions, which is precisely what you're trying to measure. It's a perfect logical loop. A snake eating its own tail. To measure the one-way speed of light, you must first know the one-way speed of light. This isn't a technical limitation we might overcome with better instruments. This is something deeper, a fundamental constraint on what we can know about reality. Professor Geraint Lewis from the University of Sydney, who reviewed the physics of this problem, describes it as a question that sits at the boundary between physics and philosophy. In October 2009, physicists Greaves, Rodriguez, and Ruiz Camacho published what they claimed was a measurement of one-way light speed in the American Journal of Physics. Other scientists rushed to repeat it. By June 2013, teams had replicated the work with greater precision. For a moment, it seemed the mystery might finally be solved. It wasn't. The experiments still relied on hidden assumptions about clock synchronization. The snake was still eating its tail. So what does this mean for everything we think we know? If we cannot measure the one-way speed of light, how do we know it's the same in all directions? How do we know light doesn't have a preferred direction in space? How do we know the universe isn't fundamentally asymmetric in ways that would shatter our understanding of time, causality, and reality itself? The answer is both unsettling and profound. We don't know. we've made a choice. A convention. In 1900, mathematician Henri Poincaré proposed what became known as Einstein synchronization, a method for setting distant clocks that assumes light travels at the same speed in all directions. 5 years later, Einstein built the entire theory of special relativity on this assumption. Not because he could prove it was true, but because it was the simplest choice. The most elegant convention. And it works brilliantly. GPS satellites navigate with centimeter precision. Particle accelerators smash atoms at exactly the energies predicted. The universe behaves as if light speed is isotropic, the same in every direction. But as if and actually is are not the same thing. By the end of this journey, you'll understand exactly why this measurement has eluded humanity for 350 years. You'll see why the problem goes deeper than clocks and lasers, why it touches the very nature of time and simultaneity. You'll discover what happens when you abandon the assumption of isotropic light speed, and why the universe might look stranger than you ever imagined. And you'll learn why some of the world's leading physicists, including Professor Clifford M. Will from the University of Florida, who has spent decades studying relativity, believe this isn't just an academic curiosity, but a window into the fundamental structure of spacetime itself. The speed of light isn't just a number. It's a choice we made about how to organize reality, but to understand why we made that choice, and what it really means, we need to go back to the beginning. To a time before Einstein, before relativity, before anyone knew that measuring light speed would reveal one of the deepest mysteries in all of physics. By the end of this journey, you will understand why the one-way speed of light remains unmeasured after 3.5 centuries of trying. You'll see why this isn't just a technical challenge, but a fundamental limit on human knowledge. You'll discover how Einstein's theory of relativity depends on an assumption we cannot verify. And you'll learn what happens when physicists dare to imagine a universe where light doesn't play by the rules we thought we knew. But to get there, we must first travel back to where it all began. To the moment when humanity first realized light doesn't travel instantaneously. To the ingenious experiments that measured its speed with ever greater precision. And to the hidden problem that lurked beneath every measurement, waiting 300 years to be recognized. The year is 1676. Danish astronomer Ole Romer sits at his observatory in Paris, tracking the movements of Io, one of Jupiter's 4 largest moons. He's noticed something strange. When Earth moves closer to Jupiter in its orbit, Io's eclipses happen earlier than predicted. When Earth moves away, they happen later. Romer realizes what he's witnessing. Light takes time to travel across space. The eclipses aren't changing, the light carrying information about them is covering different distances as Earth moves. From these observations, Romer calculates that light takes approximately 11 minutes to cross the diameter of Earth's orbit. It's the first demonstration that light has a finite speed, traveling at roughly 214,000 kilometers per second by his calculations. For the next 2 centuries, scientists refined this measurement. In 1849, French physicist Hippolyte Fizeau used a rotating toothed wheel to measure light speed across just 8 kilometers of Parisian air. Light passed through one gap in the spinning wheel, traveled to a distant mirror, and returned through the next gap. By adjusting the wheel's rotation speed until the returning light aligned perfectly with the gaps, Fizeau calculated light's velocity at 313,000 kilometers per second. 20 years later, Léon Foucault improved the technique using rotating mirrors instead of wheels, achieving a measurement of 298,000 kilometers per second. Each experiment brought humanity closer to the true value. Each result seemed to confirm that light travels at a constant, measurable speed. But here's what none of them noticed. Every single measurement was round-trip. Foucault's light traveled out to the mirror and back. Foucault's light made the same journey. Even Roemer's observation of Jupiter's moons measured light crossing space and returning months later when Earth had moved in its orbit. They were all measuring the average speed of light over a complete journey, forward and return. Professor Geraint Lewis from the University of Sydney, who has extensively studied this problem, explains it this way: measuring the round-trip speed of light is straightforward because you only need one clock. Light leaves at time 0, travels to a mirror, bounces back, and returns. You measure the elapsed time and divide by twice the distance. Simple. But measuring one-way speed requires two clocks, one at the start and one at the destination. And here's where the foundation starts to crack. How do you synchronize those clocks? The most obvious method seems simple. Place two clocks side by side, synchronize them, then slowly carry one clock to the distant location. But Einstein's theory of special relativity proved that moving clocks experience time differently than stationary ones. Time dilation means the carried clock will no longer match the stationary one by the time it arrives. Perhaps you could send a light signal to synchronize them instead. Flash a light from clock A at noon. When clock B receives the signal, it sets itself to noon plus the light travel time. But wait, how do you calculate that travel time? You need to know how long light took to get there. You need to know the one-way speed of light. You're trying to use light to measure light speed. The snake is eating its own tail. In 1900, French mathematician Henri Poincaré recognized this problem clearly. He proposed what became known as the Einstein synchronization convention, a method that assumes light travels at speed c in all directions and uses that assumption to set distant clocks. 5 years later, Einstein adopted this convention as the foundation of special relativity. But it's crucial to understand what Einstein did. He didn't prove light travels at the same speed in all directions. He couldn't. The measurement is impossible without already assuming what you're trying to prove. Instead, Einstein made a choice, a convention that light speed is isotropic, meaning identical in every direction. And this convention works spectacularly well. GPS satellites orbiting Earth account for both special and general relativistic effects, synchronizing their clocks using Einstein's assumptions. They predict your location to within meters. Particle accelerators smash protons together at precisely calculated energies. The universe behaves exactly as Einstein's theory predicts. But behavior and reality aren't necessarily the same thing. A universe where light travels at different speeds in different directions could be made mathematically equivalent to our current model through a change of coordinates. The physics would work identically. The predictions would match. Only the underlying reality would be different. This realization transforms the question. We're not asking whether we can measure the one-way speed of light. We've established we cannot. We're asking something deeper. Is the one-way speed of light even a meaningful physical quantity, or is it merely a convention we choose for mathematical convenience? Professor Clifford M. Will from the University of Florida, whose research focuses on testing general relativity, has noted that this question sits at the intersection of physics and philosophy. The distinction between a physical fact and a useful convention becomes blurred when both produce identical predictions. Yet the possibility remains tantalizing. What if light truly does travel at different speeds in different directions? What if the universe has a preferred direction we've never detected because we've only ever measured averages? What would that mean for causality, for the nature of time itself, for everything we think we understand about how reality works? The answer requires understanding not just the physics of light, but the fundamental structure of spacetime. And that journey begins with a simple but revolutionary idea that changed everything we thought we knew about the universe. 1905. A 26-year-old patent clerk in Bern, Switzerland publishes a paper that will reshape humanity's understanding of space and time. Albert Einstein's special theory of relativity rests on two fundamental postulates. The first states that the laws of physics are the same in all inertial reference frames. The second declares that the speed of light in vacuum is constant for all observers, regardless of their motion or the motion of the light source. That second postulate changed everything. It meant that whether you're standing still or racing toward a light beam at half the speed of light, you'll always measure that beam traveling at exactly 299,792,458 meters per second. This seemingly impossible claim led to time dilation, length contraction, and the famous equation relating energy to mass. Einstein built an entire edifice of physics on the assumption that light speed is isotropic, identical in all directions. But Einstein himself understood something crucial. He wasn't stating a measured fact. He was proposing a convention, a choice about how to define simultaneity across distance. In his original paper, Einstein explicitly described his method for synchronizing distant clocks by assuming light takes equal time to travel in both directions. He knew this was an assumption, not a measurement. The question was whether it mattered. For decades, physicists believed the question was purely philosophical. The round-trip speed of light could be measured with exquisite precision, and that seemed sufficient. In 1972, scientists at the United States National Bureau of Standards used lasers and atomic clocks to measure the round-trip speed at 299,792,458 meters per second, with an uncertainty of just 4 meters per second. The measurement was so precise that in 1983, the scientific community redefined the meter itself in terms of light speed, making the speed of light an exact defined constant rather than a measured quantity. This redefinition seemed to settle the matter. But it actually deepened the mystery. By defining the meter through light speed, scientists had made a philosophical choice masquerading as a physical one. They had encoded Einstein's synchronization convention into the very fabric of how we measure space. The one-way speed of light wasn't just unmeasured, it had become unmeasurable by definition. Then in 2009, something unexpected happened. Three physicists named Greaves, Rodriguez, and Ruiz Camacho published a paper in the American Journal of Physics claiming to have measured the one-way speed of light. Their experiment used a clever arrangement of detectors and claimed to avoid the synchronization problem that had stymied previous attempts. For a brief moment, it seemed the 300-year-old mystery might finally be solved. Other research teams rushed to replicate the work. By June 2013, multiple groups had reproduced the experiment with even greater precision. The results appeared consistent. The one-way speed of light seemed to match Einstein's assumption of isotropy. Science magazines buzzed with excitement. Had humanity finally broken through the fundamental barrier? The answer came swiftly from theoretical physicists who examined the experimental setup. Every version of the experiment, no matter how cleverly designed, still relied on hidden assumptions about clock synchronization. The scientists had simply moved the assumption to a different part of their apparatus, disguising it but not eliminating it. The logical loop remained unbroken. You cannot measure the one-way speed of light without first assuming something about how light travels in different directions. Professor Geraint Lewis, reviewing the problem years later, emphasized that this isn't a failure of experimental ingenuity. It's a fundamental constraint built into the structure of how we define time and simultaneity. Any measurement of speed requires knowing both distance and time. Distance poses no problem, we can measure it directly with rulers or laser rangefinders. But time across spatial separation requires synchronized clocks, and synchronizing clocks across distance requires knowing how fast signals travel between them. This realization forces us to confront something uncomfortable. The one-way speed of light might not be a physical fact at all. It might be what philosophers call a conventional choice, a definition we adopt for convenience rather than a property we discover about nature. Physicist Hans Reichenbach explored this idea extensively in the mid-20th century, showing that you could construct a consistent physics where light travels at different speeds in different directions, as long as you adjust your definition of simultaneity accordingly. Imagine a universe where light travels instantly in one direction but takes twice as long as we think in the opposite direction. The round-trip average would still match our measurements perfectly. Your GPS would work identically. Particle colliders would smash atoms at the same energies. Every experiment would yield the same results because physics depends only on round-trip measurements and local observations. The difference would be purely in how you choose to define what simultaneous means at different locations. This possibility reveals something profound about the nature of scientific knowledge. We often imagine that physics uncovers objective facts about reality, that measurements reveal truths independent of human conventions. But the one-way speed of light suggests something more subtle. Some aspects of our physical theories might be choices we make about how to organize and describe reality, rather than discoveries about how reality must be. The question becomes, does the universe have an objectively correct reference frame, a preferred direction, a built-in notion of simultaneity? Or are these human constructs we impose on a more fundamentally ambiguous reality? Einstein's theory assumes no preferred frame exists. But we've never actually tested that assumption for the one-way propagation of light. And this is where the story takes its most surprising turn. Because if we cannot measure the one-way speed of light, perhaps we've been asking the wrong question. Perhaps the real mystery isn't about light at all. It's about time itself, about what we mean when we say two distant events happen at the same moment. An understanding that requires diving deeper into the very foundations of relativity, where space and time merge into something stranger than either alone. The implications are just beginning to emerge. And they're far more radical than anyone in 1905 could have imagined. What happens when you abandon Einstein's assumption? What does physics look like in a universe where light travels at different speeds in different directions? The answer is both unsettling and mathematically elegant. And it forces us to reconsider everything we thought we understood about the structure of spacetime itself. In 1924, German philosopher and physicist Hans Reichenbach published a groundbreaking analysis that would haunt physics for the next century. He demonstrated that Einstein's synchronization convention, setting distant clocks by assuming light travels at speed c in all directions, was just one choice among infinitely many possible choices. You could synchronize clocks assuming light travels at any speed you want in one direction, as long as you adjust the return speed to maintain the correct round-trip average. Reichenbach introduced what's now called the synchrony parameter, represented by the Greek letter epsilon. When epsilon equals 1/2, you get Einstein's standard synchronization where light travels at c in both directions. But epsilon can range from 0 to 1, representing every possible combination of forward and backward speeds that average to the measured round-trip value. At epsilon equals 1, light travels infinitely fast in one direction and at half speed c in the opposite direction. At epsilon equals 0, the speeds reverse. Here's the shocking part. All these choices produce identical physical predictions for every measurable quantity. Professor Adolf Grunbaum from the University of Pittsburgh spent years analyzing this problem and concluded that the one-way speed of light is not a matter of empirical fact but of definitional convention. Different synchronization schemes are not competing theories about nature, they're different coordinate systems for describing the same underlying reality. Think of it like choosing between Fahrenheit and Celsius for measuring temperature. The numbers change, but the physical phenomenon remains identical. Water doesn't actually freeze at a different temperature depending on which scale you use. Similarly, the universe doesn't care which synchronization convention you adopt. The round-trip speed remains constant. Local physics remains unchanged. Only your bookkeeping method for distant simultaneity differs. But if synchronization is conventional, what happens to causality? The cornerstone of Einstein's relativity is that causes must precede effects, and no signal can travel faster than light. This principle prevents paradoxes where effects happen before their causes. Yet in alternative synchronization schemes, light appears to travel infinitely fast in some directions. Doesn't that violate causality? This question sparked decades of heated debate among physicists and philosophers of science. In 1977, physicist John Winnie published a detailed mathematical analysis showing that causality is preserved in all synchronization schemes, but what counts as simultaneous changes dramatically. Events that appear simultaneous in Einstein synchronization might have a definite time ordering in alternative schemes. Professor David Malaman from the University of California, Irvine, approached the problem from a different angle. In 1977, he proved a remarkable theorem. If you demand that your synchronization procedure respect certain natural physical constraints, specifically, that it should be definable using only causal relationships between events, then Einstein synchronization is the unique solution. This suggested that Einstein's choice, while conventional, might be uniquely privileged by the causal structure of spacetime. But other physicists pushed back. Professor Sahotra Sarkar and Professor John Stahel argued that Malaman's theorem simply reformulated Einstein's assumption in different language. You weren't proving Einstein's synchronization was physically special, you were choosing axioms that guaranteed it would emerge as the answer. The circularity remained, just hidden beneath more sophisticated mathematics. The technical heart of the problem lies in how relativity transforms between reference frames. In standard special relativity, the Lorentz transformation equations describe how space and time coordinates change when you switch from one moving observer's perspective to another. These equations contain the speed of light as a fundamental parameter. They predict time dilation, length contraction, and relativity of simultaneity. But here's what most textbooks don't mention. The Lorentz transformations already encode Einstein's synchronization convention. They assume light speed is isotropic, the same in all directions, in every reference frame. If you adopt a different synchronization scheme, you need different transformation equations. And those alternative equations can look radically different from the familiar Lorentz form while still describing the same physical reality. In the 1980s, physicist Asher Perez explored these alternative formulations extensively. He showed that you could rewrite all of special relativity using non-standard synchronization, and every experimental prediction remained identical. Particle lifetimes in accelerators, the behavior of cosmic rays, the operation of GPS satellites, everything worked exactly the same. The mathematics changed its appearance, but the physics remained invariant. This invariance reveals something profound about the nature of physical theories. What we call special relativity isn't really a single theory, it's a family of mathematically equivalent descriptions. Einstein's synchronization gives the simplest, most symmetric formulation. That's why physicists universally adopt it. Not because experiments force us to, but because elegance and simplicity are powerful guides when empirical evidence cannot decide between alternatives. Yet some physicists refuse to accept this purely conventional interpretation. Professor John Lucas from Oxford University argued passionately that the one-way speed of light must be a real physical quantity, not merely a definition. His reasoning centered on causation. When you flip a light switch, the light turns on. That's a causal process, not a coordinate choice. Surely the time it takes for the electrical signal to propagate through the wire is a physical fact, not a human convention. But defenders of conventionalism had a response. Yes, causation is real. But the numerical value you assign to the propagation time depends on how you've synchronized your clocks. Change the synchronization scheme and the number changes, even though the causal structure remains fixed. What's physical is the causal ordering, which events can influence which other events. The specific time intervals you calculate are artifacts of your coordinate choice. This debate continues to divide physicists and philosophers today. In 2005, physicist Tom Roberts published a comprehensive review in the American Journal of Physics, concluding that while the question has profound implications for our understanding of time, it ultimately cannot be resolved by experiment. It's a domain where physics bumps against its limits, and philosophy must take over. Professor Carlo Rovelli from the Centre de Physique Théorique in Marseille offers perhaps the most nuanced perspective. In his work on quantum gravity, he argues that our conventional notion of time might break down at fundamental levels. If time itself is emergent rather than fundamental, then questions about the one-way speed of light might be asking for precision in a domain where precision doesn't exist. The universe might not have a fact of the matter about which distant events are truly simultaneous. And this realization opens the door to something even stranger. If simultaneity is conventional, if the one-way speed of light is undefinable, then perhaps our entire framework of absolute space and time, even the relativistic framework, is still too rigid. Perhaps reality is more fluid, more observer-dependent, more fundamentally strange than even Einstein imagined. The deepest implications are yet to come. Here's the revelation that changes everything. The impossibility of measuring the one-way speed of light isn't a problem to be solved. It's a window into the deepest nature of reality itself. And what that window reveals is this: time is not what you think it is. When we say two events happen simultaneously, we believe we're stating an objective fact about the universe. You snap your fingers in New York at precisely the moment your friend blinks in Tokyo. Simultaneous. Same time. But Einstein's theory revealed something shocking. Simultaneity is relative. What's simultaneous for you might not be simultaneous for someone moving past you at high speed. Different observers disagree about which events happen at the same moment, and they're all equally correct. But the one-way speed of light problem goes deeper. It reveals that even for a single observer, simultaneity isn't a discovered fact. It's a constructed convention. You don't measure which distant events are simultaneous with your present moment. You define them to be simultaneous by choosing how to synchronize your clocks. And that choice, that definition, is what determines the one-way speed of light you calculate. This is the moment everything inverts. We thought we were trying to measure a property of light. We were actually exposing a property of time. Or rather, the lack of a property. Time across space has no intrinsic structure. No objective now extending throughout the universe. No cosmic clock ticking the same seconds for every observer everywhere. What we call time is a web of causal relationships, and how we organize those relationships into a numerical timeline is up to us. Let's make this concrete. Imagine you're in a spaceship traveling through empty space. You want to know what's happening right now on Earth, 1 light-year behind you. So you ask, what event on Earth is simultaneous with this moment on my ship? The answer depends entirely on your synchronization convention. Using Einstein's synchronization, you would say that events on Earth happening now, from your perspective, occurred 1 year ago in Earth's reference frame. The light from those events is currently halfway to you, traveling at exactly c in both directions. When you synchronize your clocks with Earth using Einstein's method, you assign those distant events a time value that makes the one-way speed of light equal to c. But suppose you adopt a different convention. You synchronize clocks by assuming light travels infinitely fast from Earth toward you, but at half speed c from you toward Earth. Now which Earth events are simultaneous with your present moment? The answer changes dramatically. Events that happened 2 years ago in Earth time are now simultaneous with your present, because the instant light signal bringing news of those events reaches you instantaneously in your chosen synchronization scheme. Same spaceship. Same physical reality. Different choice of simultaneity. Different one-way light speeds. Yet every measurement you could possibly perform, every experiment, every observation, every prediction, yields identical results. The physics doesn't care which convention you choose because only round-trip measurements and local observations have physical meaning. Professor David Malamud elegantly summarized this in his 1977 analysis. He showed that the one-way speed of light is inextricably entangled with the definition of simultaneity. You cannot measure one without assuming the other. They're two sides of the same conceptual coin, and that coin isn't given to us by nature. We mint it ourselves every time we decide what now means across distance. picture spacetime not as a static block where past, present, and future all exist equally, but as a network of light cones. Every event is surrounded by its light cone, the boundary representing all locations that light could reach from that event, or could reach that event from elsewhere. Events inside your past light cone could have caused your present moment. Events inside your future light cone could be caused by your present moment. Those relationships are absolute and observer-independent. Causality is preserved. But the vast region of spacetime outside your light cone, events that are space-like separated from you, has no definite time ordering relative to your present. Different synchronization conventions slice through that region differently, carving out different surfaces of simultaneity. Einstein synchronization gives you one slice. Alternative conventions give you different slices. All are equally valid because nothing physical distinguishes between them. This is why physicists like John Wheeler, who contributed profoundly to our understanding of relativity, emphasized that spacetime is more fundamental than space and time separately. The four-dimensional causal structure is real and objective. But how you decompose that structure into 3 dimensions of space and 1 dimension of time involves conventional choices. The one-way speed of light is just one manifestation of those choices. But wait. If light can travel infinitely fast in some synchronization schemes, doesn't that violate everything we know about relativistic physics? Doesn't it allow information to propagate faster than light, breaking causality and creating paradoxes? The answer is subtle. In alternative synchronization schemes, light does travel at different speeds in different directions. But, and this is crucial, no physical signal ever travels faster than the round-trip average. You cannot use the infinite forward speed to transmit information instantly because receiving confirmation requires a return signal, and that return signal travels slowly enough to preserve the causal structure. Professor Asher Perez demonstrated this explicitly in his 1980 analyses. He showed that while coordinate speeds can vary wildly depending on your synchronization choice, no observer can exploit those variations to violate causality. The prohibition against faster-than-light signaling remains absolute because signaling requires a completed round trip or a coordinated measurement involving pre-synchronized clocks, both of which restore the fundamental light speed limit. This leads to perhaps the most profound implication. If the one-way speed of light is conventional, what does that say about the nature of physical law? We typically imagine that physics discovers objective truths about how the universe works. Mass attracts mass according to gravity's inverse square law. Energy equals mass times the speed of light squared. These seem like facts about reality, not human choices. But the one-way speed of light reveals that some aspects of our physical theories are conventional scaffolding we erect to organize empirical observations. The scaffolding is useful, sometimes essential, but it shouldn't be confused with the building itself. The real physical content lies in invariant quantities, measurements all observers agree on, like proper time along world lines or the spacetime interval between events. Everything else is coordinate-dependent description. Professor Carlo Rovelli, in his work on quantum gravity and the nature of time, argues that this conventional aspect of time might be even more extensive than we realize. Perhaps time itself, as we experience it flowing from past to future, is an emergent phenomenon arising from more fundamental timeless laws. Perhaps the universe at its deepest level has no temporal flow, no objective before and after, only a network of causal relations that we organize into temporal narratives for practical purposes. The one-way speed of light stands as a permanent reminder of how much remains unknown. We've measured the round-trip speed with extraordinary precision. We've built technologies that depend on that measurement functioning correctly down to nanosecond accuracy. We've sent spacecraft across the solar system, navigating by the light time delays we calculate so precisely. And yet, we've never measured the one-way speed of light. We never will. Because beneath that impossibility lies a deeper truth about the universe. Time across distance is not a given. It's a choice. And that choice shapes everything we think we know about when, about simultaneity, about the very structure of now extending through space. The implications stretch far beyond light itself. They touch the foundations of physics, the nature of causality, and ultimately, what it means for anything to exist in time at all. Now you can see the full picture. Every piece of the puzzle fits together into a single, startling truth about the nature of measurement, time, and physical reality itself. When Ole Romer watched Jupiter's moons in 1676, he discovered that light has a finite speed. When Fizeau and Foucault refined that measurement in the 1800s, they pushed precision to new limits. When Einstein built relativity in 1905, he assumed light travels at the same speed in all directions. And when physicists tried to measure that assumption in 2009 and beyond, they discovered it cannot be measured at all. This isn't a story of scientific failure. It's a story of deepening understanding. Each generation of physicists revealed another layer of the mystery until finally we reached the bedrock truth: the one-way speed of light is unmeasurable because it's entangled with how we define time across space. You cannot separate the two. They're not independent quantities where one could be measured to determine the other. They're aspects of a single choice we make about how to organize causally connected events into a temporal sequence. Think back to that fundamental problem with clocks. To measure the one-way speed of light, you need two synchronized clocks separated by distance. But synchronizing those clocks requires knowing how fast signals travel between them, which requires knowing the one-way speed of light. It's circular, but not because we lack clever enough experimental designs. It's circular because synchronization and light speed are definitionally linked. When you choose how to synchronize clocks, you simultaneously choose what one-way light speeds you'll measure. Hans Reichenbach understood this in 1924 when he introduced the synchrony parameter epsilon. He showed that Einstein's choice of synchronization was just one option among infinitely many. David Malamud proved in 1977 that if you demand synchronization respect certain causal principles, Einstein's method emerges uniquely. But as Sarkar and Stahel pointed out, that just meant Malamud had encoded Einstein's assumption into his starting axioms. The conventionality remained. What physicist Adolf Grunbaum spent years demonstrating becomes crystal clear now. The one-way speed of light is conventional in the same way that choosing the prime meridian at Greenwich is conventional. It's not that light actually travels at different speeds depending on which convention you adopt. It's that the phrase, the one-way speed of light, doesn't refer to a unique physical quantity the way the round-trip speed of light does. It refers to a value that depends on coordinate choices. This explains why every measurement attempt has failed. The 2009 Greaves experiment and its 2013 replications seemed promising because they cleverly disguised the synchronization assumption. But physicists analyzing the setups found it lurking in the detector arrangements, in the assumptions about when signals were emitted and received, in the very structure of how the experiments defined simultaneous events. You can hide the assumption, relocate it, camouflage it with sophisticated mathematics. But you cannot eliminate it. It's load-bearing. Remove it and the entire measurement framework collapses into meaninglessness. Professor Geraint Lewis emphasized that this represents a fundamental limit on knowledge, not just a technical obstacle. We've reached the boundary where physics transitions into philosophy. The causal structure of spacetime is real and measurable. Light cones, the ordering of causally connected events, the impossibility of faster-than-light signaling, these are objective features of reality that all observers agree on regardless of their motion or coordinate choices. But simultaneity across space, that's not given to us by nature. We construct it. And in constructing it, we simultaneously construct the one-way speeds we attribute to light propagation. This is why all those alternative synchronization schemes that Asher Perez explored in the 1980s work perfectly well. A universe where light travels infinitely fast in one direction and at half speed in the opposite produces identical physics to Einstein's symmetric universe. Same particle lifetimes. Same GPS accuracy. Same gravitational lensing. Same cosmic microwave background patterns. Every test of relativity ever conducted yields the same results because those tests measure invariant quantities or round-trip averages, never one-way propagation. The revolution in understanding isn't that we discovered light behaves strangely. It's that we discovered time behaves strangely. Stranger even than Einstein's relativity suggested. Relativity showed that different observers moving at different velocities disagree about simultaneity. But at least each observer, in their own reference frame, could define an objective now extending through space. The one-way speed problem reveals that even that residual notion of absolute simultaneity within a reference frame is conventional. And suddenly, the 350-year mystery makes perfect sense. We couldn't measure the one-way speed of light because there's no unique one-way speed to measure. We couldn't synchronize distant clocks without assuming light speeds because synchronization and light speeds are two ways of describing the same conventional choice. We couldn't escape the logical circularity because it's not a vicious circle, it's a definitional relationship. When John Wheeler said that spacetime is more fundamental than space and time separately, this is what he meant. The four-dimensional structure of causally related events is the physical reality. How you slice that structure into space at different times involves choices. Useful choices, mathematically constrained choices, but choices nonetheless. Professor Carlo Rovelli takes this even further in his quantum gravity work. If time itself is emergent rather than fundamental, if the universe at its deepest level is timeless, then our difficulties with defining simultaneity and one-way speeds make perfect sense. We're trying to impose a rigid temporal framework onto a reality that doesn't intrinsically possess one. The framework works for practical purposes, for building GPS satellites and particle accelerators and predicting planetary orbits. But we shouldn't mistake the map for the territory. So here's what we know for certain. Light travels at 299,792,458 meters per second on round trips. That's measured, verified, and built into the definition of the meter itself. Every experiment ever conducted confirms it to extraordinary precision. That number is real, physical, invariant. But the one-way speed, that depends on how you define simultaneous events separated by distance. Make Einstein's choice and you get C in all directions. Make alternative choices and you get different speeds that average to the same round-trip value. All choices yield identical physical predictions. All are equally valid descriptions of the same underlying causal structure. This is the synthesis. The one-way speed of light isn't unmeasured because our instruments lack precision. It's unmeasured because measurement requires defining what you're measuring, and that definition is the very thing you're trying to determine. The snake eating its tail isn't a bug in our scientific method. It's a feature revealing where physics ends and convention begins. And that revelation has implications extending far beyond light itself. Implications for the nature of physical law, the meaning of time, the structure of reality, and ultimately, what we can hope to know about the universe we inhabit. Those implications are profound, surprising, and in some ways, deeply unsettling. They're also absolutely fascinating. The impossibility of measuring the one-way speed of light fundamentally reshapes how we understand the scientific method itself. For centuries, we've believed that physics uncovers objective truths about nature through measurement and experimentation. But this problem reveals something more subtle. Some aspects of our physical theories are not discoveries about reality but choices we make about how to describe reality. And those choices, while constrained by logic and convenience, cannot be validated or refuted by experiment. This has profound implications for how we interpret physical theories. When Einstein published special relativity in 1905, physicists initially debated whether length contraction and time dilation were real physical effects or merely apparent artifacts of measurement. Experiments eventually showed they are real. Moving clocks actually do tick slower, moving objects actually do contract. But the one-way speed of light occupies a different category entirely. It's neither real nor illusory. It's conventional. Professor John Norton from the University of Pittsburgh, who has extensively studied the foundations of spacetime theories, describes this as revealing the existence of gauge freedom in our theoretical frameworks. Just as electromagnetism has gauge symmetries where different mathematical formulations describe identical physics, our framework for describing time has a synchronization gauge freedom. We can choose different synchronization schemes the way we choose different coordinate systems, and the underlying physics remains unchanged. This realization forces us to be more careful about which aspects of our theories we claim correspond to reality. The spacetime interval between events is real, all observers agree on it. The causal structure of light cones is real. But the specific time coordinate you assign to distant events, that's gauge-dependent. Conventional. Not a fact about the universe but a fact about your chosen description of the universe. The implications extend even into quantum mechanics. Quantum entanglement allows two particles to exhibit correlated properties instantaneously across arbitrary distances. When you measure one entangled particle, the other particle's state becomes determined immediately, no matter how far apart they are. This seems to violate Einstein's prohibition against faster-than-light signaling. But it doesn't, because you cannot use entanglement to transmit information. You only see the correlations when you compare measurements afterward, which requires classical communication at or below light speed. But here's the question that haunts quantum foundations. When exactly does the second particle's state become determined? At the same instant you measure the first particle. But same instant across space is precisely what the one-way speed problem shows to be conventional. Different synchronization schemes place the collapse of the entangled state at different times. Yet all yield identical predictions for every measurable outcome. Professor Tim Maudlin from New York University has argued that quantum entanglement might actually require an objective simultaneity relation, a preferred reference frame that determines which events are truly simultaneous. If Maudlin is correct, then measuring quantum correlations might indirectly reveal a physical fact about the one-way speed of light by showing which synchronization convention matches the objective time structure of the universe. But other physicists counter that quantum mechanics, properly understood, doesn't require absolute simultaneity at all. The debate remains unresolved. Can we ever break through this fundamental barrier? Several physicists have proposed creative approaches. One suggestion involves using gravitational waves, ripples in spacetime detected by instruments like LIGO. If gravitational waves travel at a different speed than light, you might be able to use them to establish a synchronization standard independent of light, then measure light's one-way speed relative to that standard. But general relativity predicts gravitational waves travel at exactly the same speed as light, and observations from neutron star mergers have confirmed this to within 1 part in 10 to the 15. Even if they traveled differently, you'd face the same synchronization problem with gravitational waves that you face with light. Another proposal suggests using the cosmic microwave background radiation as a preferred reference frame. The CMB defines a special frame in which the radiation appears uniform in all directions. Perhaps this frame represents an objective standard of rest, and measuring the one-way speed of light relative to this frame would yield a unique physical answer. But this merely shifts the question. You've chosen a particular reference frame as special for observational reasons, not because physics forces that choice. The one-way speed of light relative to the CMB frame is still conventional within that frame. Professor Sean Carroll from Johns Hopkins University has noted that future theories of quantum gravity might dissolve the problem entirely. If spacetime itself is emergent from more fundamental quantum information, then classical notions of light propagating through space might not apply at the deepest level. The one-way speed question might be asking for precision in a domain where the question doesn't have meaning. Just as asking about the temperature of a single atom doesn't make sense because temperature is a statistical property of many atoms, asking about the one-way speed might not make sense in a universe where spacetime itself is an emergent approximation. Beyond physics, this problem illuminates the relationship between human knowledge and objective reality. We like to imagine that science converges on truth, that as measurements become more precise and theories more comprehensive, we approach complete understanding of how things actually are. But the one-way speed of light demonstrates that some questions science confronts cannot be answered because they're not questions about how things are but questions about how we choose to describe things. This doesn't make science arbitrary or relativistic in any problematic sense. The constraints are real. You cannot choose clock synchronizations that violate causality. You cannot invent one-way speeds that don't average to the measured round-trip value. The gauge freedom exists within strict boundaries determined by observational facts. But within those boundaries, genuine freedom remains. And that freedom reveals that our scientific theories are part description, part convention. Philosopher of science Bas van Fraassen has argued that recognizing these conventional elements doesn't diminish science but enriches our understanding of what scientific theories accomplish. They don't mirror reality like photographs. They organize our experiences and predictions into coherent frameworks that work. The framework's value lies in its predictive power and explanatory coherence, not in claiming that every element of the mathematical formalism corresponds to something objectively real in nature. Despite 350 years of progress, fundamental questions persist. Does the universe have an objective structure of simultaneity that we simply cannot access, or is simultaneity genuinely conventional all the way down? Is there a preferred reference frame defined by the CMB or quantum entanglement, or is physics truly frame-independent? Will future theories transcend these questions or reveal new ways they might be meaningfully posed? We don't know. And perhaps more importantly, we may never know. Some questions might lie permanently beyond the reach of empirical science because they're questions about unobservable gauge choices rather than observable phenomena. That doesn't make them meaningless. Philosophers and physicists will continue debating them because they illuminate the structure of our theories and the limits of human knowledge. But it does mean we must accept a certain humility about the scope of what physics can determine. Professor Carlo Rovelli suggests embracing this limitation as liberating rather than frustrating. If time is less absolute than we thought, if simultaneity is more flexible, if the universe is stranger and less constrained by rigid structures, then reality might be richer and more surprising than our intuitions suggest. The one-way speed of light stands as a permanent reminder that the universe doesn't owe us simple answers to every question we can formulate. Yet within these limitations, vast territories of understanding remain accessible. We can measure spacetime curvature, detect gravitational waves, observe the universe's expansion, probe quantum entanglement, search for dark matter, and explore countless phenomena where physics yields definite, testable predictions. The one-way speed of light is special precisely because it's exceptional, a rare instance where nature draws a hard boundary around what we can know. And standing at that boundary, looking into the unmeasurable, we glimpse something profound about the relationship between minds and cosmos. Something about the limits of knowledge. Something about the nature of time itself.